This is a pretty straightforward diffraction problem, okay? So here's our setup. We have light that's illuminating a diffraction grating. So the light is coming in, hitting a diffraction grating, and it's 550 nanometers, and 550 nanometers is green, okay? And then the light goes through the diffraction grating, and so we get a series of diffraction orders here, okay? We get m equals 1, we get m equals 2, etc. So if I was to project these on a screen, I'm going to get a series of bright spots, okay? I'm going to have something like this, okay? And we want to know what are the angles of the first two diffraction orders. What is this angle, theta 1, and what is this angle, theta 2? That's what we're looking for here. Now remember, we have this relationship. For diffraction grating, the angle of the mth order is given by this relationship right here. D, which is the slit spacing, okay, times the sine of theta m is equal to m times lambda. So the only tricky part of this problem is to know what is D equal to. What is the slit spacing? Well, the diffraction grating is 1 centimeter wide and it has 1,000 slits. And so D is just equal to the width of the grating divided by, so 1 centimeter divided by 1,000. Because 1,000 slits adds up to 1 centimeter. So when we calculate this, 1.0 centimeters is 1.0 times 10 to the minus second meters divided by 1,000, okay? I get a slit spacing of 1.0 times 10 to the negative fifth meters. Or, if I want to put it in microns, that's 10 microns. A micron, of course, is 10 to the minus sixth meters. And I'm going to put things in microns so I can compare apples to apples. The other thing I want to look at is this, the wavelength. And the wavelength of light is 550 nanometers. And nanometer is 10 to the minus ninth of a meter. So that's 550 times 10 to the minus ninth meters. Putting that in microns, it's 0.550 times 10 to the minus sixth meters, 0.55 microns. So the wavelength is 0.55 microns. The slit spacing is 10 microns. This number is significantly less than this number, and that tells us that the angles in the pattern will be pretty small. Okay, if I have a small slit spacing, I get a big spacing of the orders. If I have a big slit spacing, I have a small spacing of the orders. Okay, we know this. And so we can use that for our assessment. For our assessment, I expect these numbers to be a couple of degrees or so. Well, let's go ahead and solve and see what we find them to be. Okay, let's do two orders. First, I'll do m equals 1. For m equals 1, the first order, I just get this. I get the sine of theta 1 is just equal to lambda over d. Well, I know lambda and I know d, and so I can just solve for that. To two significant figures, I get this. I get that this angle is 3.2 degrees. For m equals 2, I get the sine of theta 2. Okay, now I have a m equals 2 in here is equal to 2 times lambda over d. So it's just double what it was previously. That leads to an angle which is approximately double of the previous angle, 6.1 degrees. So those are the angles of my first two orders, 3.2 degrees, 6.1 degrees, two significant figures. My assessment is this. We said, given that the slit spacing is big compared to the wavelength, we expect these angles to be small, and these angles are small. They're just a few degrees, and so our net result matches what we understand about how the world works, and so everything's good.